Hello guys, welcome back to Manala's Arc. My voice is back now. If you watched the previous video, part 1 of this video, you will be aware that my voice was bad on the previous video, and I know it's terrible to hear or to listen to someone whose voice is not perfect, right? But then today I'm here guys, I'm back and I'm ready to talk for hours now. Okay, again, welcome back to Manala's Arc, guys. This is part 2 grade 10 probability video. On the previous video, I've covered the probability of an event, reduced sample space, relative frequency, Venn diagrams, right? Today, I will continue with Venn diagrams. And in case you don't know what I'm talking about, please go to your YouTube channel, search for Manala's Arc, enter the channel, and sorry for my signal being slow there. This thing will take you to my, I don't know what they call this, my dash. Yeah. So you go to playlist and then this will appear here. I want you to get to the playlist and choose this part of grade 10 probability. Now here you're going to select this part and then it's going to take you there. And then voila. Here it will go, right? So what you will see is that on this playlist you will see 3 videos. One that I did in which year was this? 2023. Another part 2 video whereby I'm solving previous papers that are still 2023, and then there is this one here. This one is the one that I did yesterday. So when you open it, it will show this way, and this is the part 1 of this video that I'm recording, in which this one that I'm recording, it's part 2, right? So I just wanted to show you where you get this so that you don't get confused, or you can just go and type. Let me remove this so you can see it. You can just go ahead and type grade 10 2024 probability lesson part 1 from Manala's Arc. You will see that. So guys, I hope you won't suffer when it comes to that. Now we can move on to the video of today. So now here, the things that I want to cover today. It's a few things, but I want to start with this question that I left you with before, right? So let's get to solve this part here. So here on this part here, let me choose a pen, a black pen with a small ink. Okay, it says a 12-sided die is rolled. I hope you can see that. The following events are defined. You have event A, you have event B, right? That's a 12-sided die. So let us start with the sample space. I want us to start things properly. The set notation of the sample space is the following. Remember, this is a 12-sided die. So it will have all the numbers from 1 up until 12. That's the sample space. And then we have event A. What is event A? Event A looks like this. Oh guys, it feels good recording this video with my voice back. It's so amazing. The first 5 prime numbers. What are prime numbers? Numbers that have only 2 factors. I know somewhere, somehow, there is someone who will believe 1 is a prime factor. I bet I'm not the one who taught you maths, chief. A prime number can never be 1. Okay? So, our prime numbers that we have, I have a 2, I have a 3, I have a 5, I have a 7. 9 is not a prime number. Please be careful. And then I have an 11. What did they say? They said the first 5 prime numbers, and we have 1, 2, 3, 4, 5, which makes sense, unless you thought 1 was a prime number. So, and then here, what do we have? I write them down. I have 2, 3, 5, 7, 11. 1, 2, 3, 4, 5. Yes. And then event B. Now I write event B in set notation. Right, event B, it says the first 2 multiples of 6. Bear in mind, I haven't started answering the question. I'm writing these things down so that when I get to answer the questions, I don't suffer at all. Event B, the first 2 multiples of 6. Now, what are multiples of 6? I bet you know those things. I don't need to explain that. The first one, I'll say it's 6. The next multiple of 6, it's 12. Those are the only 2 multiples of 6. Right. Okay. Now it says write down the set A. Write down the set A. I already did that. Write down n of A. I must do that. Okay, let's do that. Number 1, the number of values that are in A. That's what n of A means. My pen is buffering for some reason. How many items are in A? I have 5 items in A, right? And then now to the next. What is happening with this pen? Guys, please let me solve this. Such disrespect. Can't believe I can be disrespected by a pen like that. Why is it buffering? Okay, it's writing now. Okay, we're back at it, guys. Let me remove that. Okay, we said n of A is 5. I have 5 items in A. And then afterwards, this question wants, what is happening here? It wants the probability of A. Right? Write that. Now, let's erase that because it doesn't want to write that. Probability of A is amount of items. Let me show you. The number of items that are in A over the number of items that are in the sample space. You always start with the formula. How many items are in A? We have 5 items in A. How many items are in the sample space? We have 12 items in the sample space. Easy as that. Marks there. Marks there. Venn diagrams, it's not all about drawing Venn diagrams. Sometimes it's about answering questions that might be in the Venn diagrams, right? Okay, number 2. It says, write down the set of n of B and the probability of B. Okay, I already wrote the set of B. There it is. And then n of B, it basically asks me for the amount of values that are in the set B. That is 2, right? In B, I only have 2 items now. The probability of B, something is wrong with this thing here. Probability of B, it's said to be, you always start with the formula, n of B all over n of the sample space. That is, how many items are in B? I have 2 items in B. How many items in the sample space? I have 12. Now, your probability values always have to be in the simplified form. I want you to grasp that, guys. Make sure you don't forget that. Your probability values are always in the simplest form. So 2 over 12 is the same as what? It's the same as 1 over 6. So there we go, right? Then now we go to the next questions, whereby we have to draw Venn diagrams to represent the actual outcomes and things and that, right? Let's do that now. Let me clear some space here. Now, with the previous questions that we had, our Venn diagrams were pretty simple. We had intersections. It was easy for us to write down things that have intersections. Now we have events that have no intersection. I hope you remember what's an intersection. So when I'm looking at this value here, there's no value that exists in A and it exists in B. So which means now, if I have my sample space here, let me not be too much here because I need a lot of this space. Which means when I look at that, this is my Venn diagram here. Right? And remember to put an S for sample space. It always needs to be there. I realize that I have event B. Let me do a small circle for B here. Boom, boom, boom. There is B. The first Venn diagram I must do, it must be which type of a Venn diagram? Actual outcomes. I must show the outcomes. So which means in event B, the outcomes it's 6, it's 12. Right? Hope it's visible there. And then I have event A. Nobody said when you draw a Venn diagram, the circles are supposed to be equal. It doesn't really have to be that way. Okay, here in this case, I have 2, I have 3, I have 5, I have 7, I have 11. Is that it looks like an 11 now, right? So what is missing? A number like 1 is missing, right? So 1, 2, 3. A number like 4 is also missing. So I put 4 in the rest of the sample space there, right? And then 5, 6, 7. A number like 8 it's missing, so I put it there, right? 9 is missing, so I'll put it there outside. Guys, this pen around this area, it doesn't want to write. I have a number like 10, I put it there. 11, then 12. So any number that's not in event A, we put it outside this box here. But I'm sure you know that by now, right? And then what else do we have? Question 4, it says draw a Venn diagram to represent the number of outcomes. So right here, number of outcomes. Let me fix my pen. It's really misbehaving. Okay, let's see now how it behaves. It seems like it's flowing. Perfect. Oh, now, okay. Here's my sample space. The pen feels good now. Okay, the Venn diagram that I want now, it's the one that shows number of outcomes. So right here, I'll do event A, I'll do event B there. So here's A, here's B. How many things are in B? I have 2 values in B. How many values are in A? I have 1, 2, 3, 4, 5 values in A. Right? Then how many values are in the rest of the sample space? This, again, bear in mind, this area is called event A. This area is called event B, this circle here. But this area here, this space outside, it's not called the sample space. The sample space, it's everything that you see inside this rectangle here. That's the sample space. This space here, we just call it the rest of the sample space. The other part, you see event A. The other part, you see event B. The other part, it's the rest of the sample space, right? So the rest of the sample space, it has 1, 2, 3, 4, 5 values. Which makes sense because these items all together, they add up to 12, which is the 12-sided die, right? Now, question 5, quick, let's create space for question 5. So in this case, on this Venn diagram, what I need now, this pen writes so smoothly now, perfect. I have event A, I have event B. Remember, the circles do not cross because they don't share any values. A probability Venn diagram, it's supposed to add up to 1. We are on the last question now, in case you are lost, right? A probability Venn diagram is supposed to add up to 1. So in this case, I'm saying my sample space is equals to 1. Why? Because this is a probability Venn diagram. In this situation, I was doing the number of outcome Venn diagram, which means my numbers should add up to 12, right? So now here, what happens? I need some space for rough work, but we'll do it. Starting with this one, the rest of the sample space. The probability here is that there are 5 values out of 12 numbers in the sample space. And this is the simplest form, so it doesn't need to be simplified further, right? And then here I have 5 values in event A out of 12 values in the sample space. So this also is the simplest form. It doesn't need to be simplified further. Now, however, for this situation here, I have 2 values. Let me write it here. 2 values out of 12 items. Now that can be simplified further into what? Into 1 over 6, right? So which means now the values that I'm going to write here is 1 over 6. Be good. So this is your probability Venn diagram. This is your number of outcome Venn diagram. And the other one that I just removed was the actual outcome Venn diagram. Hope be good there. So the next part now, which is what's supposed to be today's work. It's me now talking about unions and intersections, right? So I want to take a scenario to build this concept for you of unions and intersection. So I think there's some question that we did here. Let me see if I can scroll back through these notes and see if I can borrow a question right here. This is beautiful. I can work with this. Let me put it here. We will use it here. Perfect. So now, for us to discuss the concept of unions and intersection, here we have a Venn diagram, right? In this Venn diagram, what we have, it's the following. Let me write it down for you. First of all, we have the sample space. What does the sample space have? Guys, this pen doesn't write properly today. Like, I'm so disappointed. In the sample space, we have A, B, C, D, E, F, G, H, I, J, K. Do we have an L? Yes, L, and M, and N. Right? There's no O, so it ends here. That is the whole sample space. Everything that ever exists in this Venn diagram comes from these items here. Now we have event A. Event A, what do we see? We see that in here we have A, we have B, we have C, we have D, and we have E. Right? Up until the A, B, C, D, E only. And then we have event B. In event B, I have F, G, H, I. It ends there, right? So that's event. And then we have event C. In event C, we have J and K. I'm separating these things with a semicolon, right? So I'll get to the point. You'll see it, right? So now we start talking about things that we call intersections. What is an intersection? When we talk about an intersection, we are talking about a point that is being shared between two events. Only that point, the shared point between two events. So if you look at it here, this thing is not a highlighter. What is it doing? Let's check a highlighter maybe. Here's a highlighter. So if we check here, B and A, they share these 2 points here, and you can also see it here. B. Oh, in event B, I missed something there. Oh, guys. Oh, good Lord. In event B, there are some outcomes that I'm missing. We don't just have 4 things in event B. We have 6 things. Let me put it there properly. In event B, right, we have D, we have E, we have F, G, H, I, right there. In event A, we have A, B, C, D, E, right? And event C, we have J and K, right? So those are the things we have. So what I wanted to say here is that in this situation, we have this part here. And this part here is the intersection. When we say this part is an intersection, we are saying event A and event B. This is the only thing they have in common. So they have D and E in common, right? Same thing applies here. In this set notation, I have B, D, and E, right? So these 2 things, this area here that is being shared between A and B, we call it the intersection. I don't know why my bot doesn't want to write there. Okay. That is the intersection. So our intersection, we write it this way. The intersection of A and B as a set notation, it is D and E. That is the intersection. Right? We good there. Your notation is going to be A and look at how I write the N. I didn't say N with a stock and then this. No, I just said N this way. Right? That's the intersection. I hope we good. Another word we might use for the intersection, we might use the word end. We might write it this way. Is it A and B? The set notation for A and B, it's D, E, right? So here, either we write it this way or we write it this way. Trust me, you will need to learn this first one properly. And you will need to understand that this and this one above, they mean intersection. It's the same thing, right? So an intersection is a shared point between 2 events. Now, let's get to what we call the union. So now, when it comes to what we say is the union, some people say it's the union, some people say it's the union. I feel like things are easy to remember when you call it like you see it. It's the union. Okay, the union now is, when we say the union of A and B, we are going to put it this way, A-U-B. That's the notation. And then when we say A-U-B, we are talking about something that is either in A or B or both, without writing the same thing twice. Let me show you what I mean by that. Look at this Venn diagram here. In this Venn diagram, what's in A? What's in A? It's A, B, C, right? So we write there. We have A, B, C. Because it's the union of A and B, I want to see what's either in A or B or both, right? So this is in A, right? And D and E are also still in A, right? They're still in the circle of A. So I can highlight them this way and say D and E. And now what's in B? What's in B? It's D, it is E, F, G H I. There. This is in A, this is in B. However, in this situation, I have a repetition now. Look at this. I have a repetition and I cannot write the same thing twice. So I'll cancel one of them because I don't want to write the same thing twice. So the union is what's in A or B. So this is in A, this is in B, this it is in both, right? So that's the union. Another wording we can use for the word union, we can say A or B. So that is A, B, C, D, E, F, G, H, and I. So that's the union. So we have the intersection, we have the union. You always need to remember those two words very much, very, very much, right? So now let's get to the other part. This pen today, it's misbehaving. I don't know why. Okay. Now, when it comes to events, guys, there are different types of events. There are events that we say are mutually exclusive. Now, what do we mean by mutually exclusive events? Now, when we refer to mutually exclusive events, we are talking about events that have, let's say it in terms of a Venn diagram. Events that have no intersections. They have no shared outcomes. Their circles do not join at all. So if I'm to put this in a Venn diagram, I'll say I have event A, I have event B, this way, inside a sample space, and they are disjoint. Let me use the word disjoint. How do you write disjoint? Okay, they are disjoint this way, right? The circles do not touch, simply put, right? So in this situation now, for you to get the probability of the intersection, remember what's an intersection? I hope you do. The probability of the intersection, we are saying it's 0. Why? Because we are saying the chances that you will get an item inside this sample space that exists in event A and event B, it's 0, because there's no such thing that an event is in A and it's in B, because the two events are separate and they have no shared outcomes, right? So the probability of that is 0 this way. And then we say the probability of the union. I hope you remember what's a union, right? So what are the odds that you will find an event either in A or in B? For you to get the value of that, you're going to use the formula, the probability of A plus the probability of B, just like this. I hope you're good there. This is for mutually exclusive events. I hope it makes sense, guys. I'll come back to these things over and over again just to add more items. But now let's move to the next one, right? So the next one that I have now, it's the following. Oh, before that, there is something that we call the general rule. The general rule of probability. So the general rule of probability says, if ever you are looking for the intersection of something, you are going to take the probability of A, add it with the probability of B, minus the probability of the union. This way. Intersection is equals to probability of A plus probability of B minus probability of the union. I hope we good there, right? I hope we good. So this applies, this formula here applies in everything. Everything probability. Every Venn diagram, you can use this formula here. Hope you get what I'm saying. In any Venn diagram, you can use this formula here, right? Let's move on to the next part. The next one we want to talk about is exhaustive events. Let me use a pen here. We have exhaustive events. So when we talk about exhaustive events, we are talking about two events that actually do not need a sample. The sample space box, right? Remember how Venn diagrams are. Venn diagrams, you have an event here, you have an event here, you have an event here. Let me fix that. Venn diagrams, you have an event here, you have an event here, and then you have things that are not either in event A or event B. So they are lingering somewhere around here in the rest of the sample space. So something can either be here, or it can be here, or it can be here, right? That's how Venn diagrams work. However, for exhaustive events, we are saying these two events, they only exist either in A or they exist in B. This way. And that's the whole sample space, this thing here. These two events are the whole sample space. You don't need the box outside. So something either exists here or it exists there and nowhere else. Right? Another situation might be this one, whereby you have this and this. You have event A and you have event B. Something either exists here, here, or there, and that's your whole sample space and nothing else. Right? So we call this exhaustive events, which means the two events, they exhaust the whole sample space. There's nothing outside those two events, right? So in this situation, what we know is that the probability of A or B is equals to the probability of A plus the probability of B. You'll get these things later on. And then the probability of we'll get to the other part, but this is what you need to know for exhaustive events. So your exhaustive events, they can be disjoint or they can be joint. This way, there are two types of exhaustive events: the ones where the circles touch and the ones where the circles do not touch. But these two events, they don't have any items outside the two events. It's either something is in A or it's in B. Something is in A or it's in B and nowhere else. There's nothing lingering outside these two events. Be good? Now, the last event now, it's us talking about complementary events. So complementary events, remember we said we have mutually exclusive events, right? What were mutually exclusive events? Mutually exclusive events were the type of events whereby you have event A here and you have event B here, and then you have the rest of the sample space enclosing there, right? So they don't touch. We just know that they are what? Disjoint. And then we have what we had what is the other word? Exhaustive events. We said we have exhaustive events in which, in this situation, what were exhaustive events? We had two types of exhaustive events. We had this event here. I'm sure you feel like they're touching. Let me remove that properly and write it there. We have this A and B, and then we had a and this is the whole sample space this way, or you had A and B this way, and that's the whole sample space, right? However, what is unique about exhaustive events? We know that the probability of A plus the probability of B is the probability of the whole thing, that is the sample space. Right, that's the unique thing. There's nothing outside these two events. It's either A or B or nothing, right? And in this one, what is unique about them? The only unique thing is that they never touch. Mutually exclusive events, they never touch. Now, when we talk about complementary events, we are talking about the combination of what's unique here and what's unique here. When you combine their two unique items, you get complementary events. What do I mean by that? So complementary events are events like this one here, which do not touch, number one. So we are taking this special character of this event. They are disjoint, right? That's one special character we took from here. Number two, we take a special character here, whereby we are saying there's no sample space, whereby probability of A plus probability of B gives you the whole sample space. We all get that, right? So now, this is what makes complementary events unique. Number one, they're supposed to be disjoint. Number two, the probability of A and the probability of B should make up the whole sample space. We good? So now, I need us to move to two things. So for those two things to happen, I need you to remember what we spoke about. And it's very, very important for you to remember these things. Let me choose a black color here. So remember we spoke about the intersection. So when we have two events, we usually write the intersection as probability of A and B. Let's not even say the probability. It's just A and B, or it is A and B in words. And then we said that we have the union. And then for the union, the notation is AUB, or we can say A or B, right? Here we are talking about shared outcomes, what is shared between the two. And then for union, we're talking about something that is in either A or B, but don't count the same thing twice, right? And then we spoke about other things also, like the general rule of probability. In this situation, we said the general rule of probability is probability of A intersecting B is equals to the probability of A plus the probability of B minus the probability of their union, right? Another way you can rewrite this, you can say the probability of the union is equals to the probability of A plus the probability of B minus the probability of the intersection. Here, the intersection is the subject of the formula. Here, the union is the subject of the formula, right? So, however, there is something you need to bear in mind now. We have things that we said are mutually exclusive events. Now, mutually exclusive events, we said, what are those? These are two circles that do not join this way. In that situation, there's no intersection at all. There's no intersection. So which means if I was to use this formula here, the probability of the union, and I'm looking for the union, I must understand that the union is equals to the probability of A plus the probability of B from this general equation. And in this part here, it's the intersection. However, we said this doesn't have the intersection. So which means on the portion of the intersection, I don't put anything because these mutually exclusive events do not have intersections. So my formula will end here. Will it be wrong for you to write it this way? No, it won't be wrong. It will still be okay. However, it's not necessary. The best way it's this way. However, if you understand the first part, you can continue with the first part. Right. And then we had things that we said are exhaustive events. Let me write that down for you. For exhaustive events, we said these two events, they make up the whole sample space. So here's event A, here's event B. These are also Venn diagrams, by the way, in case you didn't know. And that's the whole of the sample space. So something exists here or there, and there's no rectangle around them, right? So one thing we know is that in this situation, for me to get the probability of 1, I must add this, I must add this, and I must add this. I must add 3 things, right? However, here, for me to get the whole sample space, here is A, here is B, I must add this and this only. There's nothing outside them because they make up the whole of the sample space. So for exhaustive events, the rule that you're supposed to remember is that the probability of the union is equals to the probability of A plus the probability of B. Extra information to that. You're supposed to know that the probability of their union makes up the whole thing. So it equals to 1. Remember we said the sample space is equals to 1 in the probability Venn diagram. Are we good? So these are other rules also you're supposed to remember. Very much. We good? So I'm moving on from that now. I'm going to another concept that we call the rule of complements, in which this is one of the things that people forget a lot of times, and it's so important. And when details comes up, you're supposed to remember this type of things. Let's go to it. So the rule of complements. Now, the rule of complements, now this is simply mathematizing, right? This is simply mathematizing you now. Saying if this is not this, then it's that. Like, you'll get what I'm saying. The rule of complements says, if I have two events, here we go. It's just a normal Venn diagram. I have A, I have B there. The rule of complements says there is something that we call the probability of A. Right? What is the probability of A? The probability of A speaks about items that are here over everything that's in the sample space. Just right here. Right? So, what's not in A? Pa. This area and this area, they are definitely not in A. We agree on that. So, we call those things the complement of A. So we write it this way. A prime. You see that one thing, that exponent one that is there. We call it A prime. A prime. Right? So A, you just write it normally as probability of A. What is not A, you write it as the complement of A. We good? Hope you understand that part so far. So now, there is something that we say now. If I do not have A, but I have everything else that is not A, then I can find A. You see that? So I'm saying now, A, the probability of A, if I have to find it, I'm going to take the number 1, because that's the sample space, and remove everything that is not A. Now, what is everything that is not A? Everything that is not A, it's called the complement of A. This way. That's the equation. You see this equation? You see how it's formed? So which means for me to get this, I can take this and subtract this and this to get that. All set? Hope it makes sense. I can also say now, the probability of A plus the probability of what is not A is going to give me 1. Does it make sense? Because this is A. Right? This is not A, this is not A. So if I add all of these things together, I must get the sample space, and the sample space is 1. Are we good? I hope it makes sense. So again, when you have exhaustive events, this is mathematizing now. Remember, exhaustive events, this whole thing makes the sample space. I'm saying in this situation, let's call this complementary events per se. Exhaustive events that are mutually exclusive. Complementary events. Exhaustive events that are mutually exclusive. In this situation, there's no rest of the sample space. Either something is in A or it's in B, and it's disjoint. What I know is that the probability of A, it equals to 1 minus what is not A, complement of A. We good? Fairly enough. That's what we said before, right? I also know that the probability of A plus the probability of B is equals to 1. Right? Fair enough. I also know that the probability of B is equals to the complement of A. Because if this is A, then what is not A, it's here. The complement of A, it's dead. And if this is the complement of A, this is also B. B is the complement of A. We get that? So, this is maths now playing games on you right now, right? But I hope you get it. Let's get to the question so that you see how are these things applicable. Where do you get to use them? Why are you supposed to remember them this way? Complements, 1 minus this, it equals to that. Why do you have to remember those? Let's get to the questions. So here is this question here. This question, it says, if probability of A is 0.3 and probability of B is 0.4, where A and B are mutually exclusive events, then determine this, determine that, determine that. You see that? This is how these probability questions now will come to you. Make sure you are able to solve them. Now, they told you the probability of this. Let me use a highlighter here. They told you the probability of A. Fair enough. Important information. They told you the probability of B. Oops, let me charge this fast. And, okay, here is B. Let me highlight that. They told you the probability of B. And then another important thing that they told you is that these two events are mutually exclusive events. Right there, that's your ticket to a lot of things. So now, when they want the probability of A and B, what is A and B? A and B is the intersection, and we write it this way. If two events are mutually exclusive, what is their intersection? Well, mutual events are like this. It's circle A and circle B. The circles do not touch, so they don't have an intersection. So the probability of the intersection is 0. Answer for question number 1. You don't need a lot of things. You don't need to complicate things. This is how it is. You just need to remember the previous points that I told you in the other slide. Afterwards, it says it wants the probability of B. Let me erase this. For the probability of B, I mean A or B, what is that? That's the union. Remember, A or B, it's the union. Now, how do you find the union? For you to find the union all the time, use the general rule of probability minus the intersection. In which, if you listen to me in the previous slide, you will understand that you don't need to write this last part here. Okay, so now to get the union, you're going to say probability of A, here's probability of A, check, 0.3, plus probability of B, here's probability of B, check, 0.4, minus probability of the intersection. What is it? We don't have the intersection, it's 0, so you put 0 there, check. Now the probability of your union is equals to 0.3 plus 0.4, that is 0.7, easy as that. See how nice is that? Now, the last question, C, it's supposed to be in ABCs. This is supposed to be the most interesting one now. But if you write it in the proper notation, then you will get what this is. So it says the probability of not, right, A or B. So how do we write A or B? Let me put another bracket here. It's A union B, close bracket. That's A or B. Now, if it's not that, then this whole bracket has a prime here. You see that? Now, eventually, when you study these things hard enough, you will be able to do them without drawings. But for now, let me do them with you with drawings. So I have event A, I have event B. They just told me that they are mutually exclusive, so it means they might have a box here, this way. And then here's the sample space. This is A, this is B. It's a probability Venn diagram because I'm given probabilities. I'm not given actual outcomes. So on A here, I have 0.3. On B here, I have 0.4. The sample space is supposed to be equal to how much? 1. You see that? Now, if this is 0.3, this is 0.4. In total, that makes 0.7. Where's the other 0.3? It's here. In the rest of the sample space. Now, let's start with what we have and what they want. So, they want the complement of the union. What is the union? Let's start there. The union is something that is either A or something that is B. That's the union of A and B, right? So they want what is not that. So the only part that is not that, it's this area here that we didn't shade. So the complement of the union, it's the rest of the sample space. So this answer here is 0.3. See how beautiful is that? How else could we have solved it without using Venn diagrams? You could have said the complement of the union right there is equals to 1 minus what is the union, right? The rule of complements. Remember what we said about complements? Is it here? Right, yes. That you can, for you to find something, you can say 1 minus what is not that, right? So same thing applies here. For us to get the union, we can say 1 minus the complement of the union. For us to get the complement of the union, we can say 1 minus the union, right? So now here, this is equals to probability of the complement of the union is equals to 1 minus what is the union? The number for the union, we found it here. Here it is, 0.7. 0.7. We avoid small mistakes. 0.7, which is equals to 0.3, as we found it here on the Venn diagram. So you can use this method of the Venn diagram, or you can use this method of calculations. Either way, it's fine with me. We good? Let's move in another example. Here's another question. Please try to see if you can pause the video and solve the question on your own before you proceed to see my solution, right? So here, let's start with the highlighting process. Let's use green this time. They're telling you that two events are mutually exclusive. That's number one. That's a statement, a bold statement. Number two, it tells you what is not A. The complement of A is 0.3. Afterwards, they tell you the union, that the probability of A or B is equals to 0.8, right? Very much interesting. Let's start with A now. It says determine the probability of B. So two events are mutually exclusive. Firstly, what do we know? For mutually exclusive events, what we know is that they do not have an intersection, which means the intersection is 0. All set? I hope we're good. Therefore, it means now, this is interesting, if ever I'm to look for their union, I can simply say the probability of A plus the probability of B, and then I don't have to say minus the probability of the intersection, because the intersection is 0 anyway. We just said it here. Right? From the this comes from the general rule of probability, right? So this part is out already, right? So again, in this situation, two events being mutually exclusive, let's put it this way. Here is A, here is B, there, A and B, boom, 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 this way, right there, right? So what can I say here? I'm given the probability of the union, which is this and this all together, they make 0.8. And then I know that there's a situation whereby I don't have A. It says, no, how do I put this? The complement of A, which means what is not this, which can be this and this. I just know that that thing adds up to 0.3. So let me write it here. Probability of I'm talking about the statement here. Probability of not A, which means the probability of the complement of A, it's equals to 0.3, right? But what else do I know? I know that if I have the complement of A, then I can find A, right? I know that probability of A is equals to 1 minus the complement of A, from those things that we did in the previous slide. So substitution from here, I can say 1 minus 0.3, that gives me 0.7. So there I have my A. Voila. Right? So since I have A now, I can come back now and use this formula here. Oops, that is too much. What can I use? Perfect. I can come back and use this formula here to get A now. Why? Because I have the union and I have A now, therefore I can find B. Right? So I'm going to say now, let me rewrite it again. The probability of the union is equals to the probability of A plus the probability of B. Right? What is the union? The union here it's 0.8. Is equals to, what is the probability of A? We just found it here. It's 0.7. Plus the probability of B. Now I only have to solve for B. I'll transpose this to the other side. I have 0.8 minus 0.7, which is equals to the probability of B. Therefore, now I can say the probability of B is equals to 0.1. See how nice is that? Beautiful. And then question B says, explain why A and B are not complementary. Now, firstly, what do we know about complementary? Complementary, they combine mutually exclusive and what is this other one? Exhaustive events. First of all, they have to be disjoint, right? Which means they shouldn't have an intersection. Tick, that's a tick, right? Because they actually do not have an intersection. And then number two, the probability of A plus the probability of B should give us the sample space, which is 1, right? So do I have the probability of A and the probability of B? Yes. So let me see. Probability of A plus probability of B is equals to, what is probability of A? Where's my A? Here it is, 0.7. I have 0.7 plus, where's my probability of B? Here it is 0.1, 0.1. Therefore, probability of A plus probability of B is equals to 0.8. Right? I can say, therefore, they are not complementary. Why? I don't even have space to write all that sentence. Why? Because the probability of A plus the probability of B is not equals to 1. Right? According to this part here. So these two events are not complementary because when I add the two events, they don't add up to 1 for me. Is that proper? Let me do the last one because I see now I'm on 53 minutes. Here's the last one. It says, if probability of A is equals to 0.25, probability of B is equals to 0.5, and probability of the union is equals to 0.625. Calculate the probability of the intersection. That's question 1, right? Let's do that. You see how I read these things? I call this thing intersection. I call this the union. And this is the probability of A and B. Right? Use those ways around these things so that you don't get lost. Right? Starting with the intersection. They want us to calculate this. The intersection, right? The formula for that says probability of A plus probability of B minus probability of the union. This way. For me to get this intersection now, I'm going to say intersection is equals to, what is probability of A? 0.25. What is probability of B? 0.5 minus, what is the union? 0.625. And that, if I have to use my calculator, it will give me, where's the calculator? Let's do this. 0.25 plus 0.5, so 0.5 minus 0.625, that is 0.125. Hope I didn't make a mistake there. Yeah, I didn't. 0,125. Let's write it down. That's the answer now for A. Usually the exam says to 2 decimal places, so this is 0,13 according to exam conditions, because we usually answer to 2 decimal places. Number 2, but make sure that you pass through this step and then you give us this as your final answer, just to follow the exam instructions. But pass through this part first. Don't just skip from here and give us a rounded off version. Good. Now, question 2, it says, are the events complementary? Give reasons, right? So first things first, I expect you to tell me that these events, they are not complementary. Why? Simply put, because complementary events, because complementary events have the probability of their intersection being 0, right? But in this case, the probability of A and B is not equals to 0. That is why they are not complementary. What do we mean by that? We are saying if I have event A and event B on a Venn diagram, there is no intersection here. Therefore, the probability of their intersection, as we've been saying for mutually exclusive events, probability of intersections are supposed to be 0. But in this situation, the probability of our intersection was 0,13. It was not 0, which makes this event not to be complementary, because complementary events are mutually exclusive events. We good? So I'll throw you with the last one, but I won't solve it with you. So I hope you'll be able to solve that question on your own. And then those of you who are in the group with me, you can share the solutions with me on WhatsApp, right? So here's my parting shot. A smoke detector system in a large warehouse uses 2 devices. Read the statement and see if you can answer this question based on your probability understanding. And this is a level 4 question, so just try it and see if you can win. And I'll wait for your responses. If you can respond in the comment section, you can do that. If you can inbox me, you can do that, right? So there you go, guys. I hope you enjoyed this video. I hope you learned something from it. The next video that I'm looking forward to do is the video that has to do with solving past papers, probability questions from past papers. That's what I'm looking at. Okay, goodbye. Thank you for watching this video up until here. If you haven't liked this video, you can do that now. And then if you haven't subscribed to the channel, you can also do that now. Goodbye.